Hi, it's Carly McAvoy. I'm doing homework 6B, the second half. Well, not exactly the half, but 12 through 17. And we're starting with this problem talking about the normal quantile plot. This plot, when you look at the x, we're talking about an x value given in the data set, like 202, 151, etc. All of these are data points that go along the x value. And then the y value, or the vertical axis, is the z-score. That's what a quantile plot is, talks about the z-scores. And so what they're asking here, examine this and determine whether it depicts a sample data from a population with a normal distribution. If it's a normal distribution, the data will have will form a line, and it won't have any other non-line shape to it. So I would say this one, the distribution is normal. The points are reasonably close to a straight line and do not show a systematic pattern that is not a straight line pattern. That's what I think, because it looks like it. Pat looks like a line to me. Yep, that's number C. Okay, I need to shut that off. Okay, so then this next one, examine the normal quartile plot, determine whether it depicts a sample from a population with a normal distribution. Again, quantile plot is an x compared to a z-score. Notice your z-scores they have going from -3 to +2. The z-scores that we see most of the time, 95% of the time, are between 2 and -2, right? Anyway, this one, see how you have a point down here and a point down here? We're starting to get a shape that's not that linear. So no, the points do not lie close to a straight line. They don't fit that line. The straight line being this. Notice that it's, well, anyways, let's just move on. It was number 14. I deleted that one, so we're going to jump on to number 15. Okay, so number 15, use a normal approximation to find the probability of the indicated number of voters. In this case, assume that 171 eligible voters aged 18 to 24 are randomly selected. Suppose a previous study showed that among eligible voters, 22% of them voted. Find the probability that fewer than 43 voted. We want to do a normal distribution like we have been doing. It's a little different because we're talking about binomial distribution, but we want to know what our mean is, and then we want to know where 43 fits into that mean, and then we want to find the probability, which is going to be normal CDF. In order to get a normal CDF, you should know by now that we need to know what mu is. We need to know what the standard deviation is. N times P is our mu, and the square root is NPQ. Remember how to get Q? 1 minus P. So we want to find those two values so that we can then answer the question. Well, I will tell you what those two values are. What is our N? I guess I should ask you that. The N is the number of eligible voters. So we have N is 171. Times the probability of 0.22, and over here for the standard deviation we have 171, 0.22, and 0.78, multiplying those two things together. So I did that down here earlier, and I got 37.62 for our mean, and so that means that in the middle of our diagram here, or up here, I could put it 37.62 as our mean. And our standard deviation is 5.4, that must be a 2, written very poorly. And then we want to know what's the probability of getting fewer than 43. So 43 is over here somewhere, and we want to get fewer than that. But because we want fewer than 43, we don't want exactly 43. And so what we do is we subtract off 0.05. Oops, I did 0.5. 0.05 off. So that gives us 42.95. So we do this little subtraction thing. So it's a little bit to the left of that. So what I'm going to put into my normal CDF, I'm going to put my mu of 37.62. I'm going to put my standard deviation of 5.42. And I'm looking to the left, which means I have -1 to infinity on the left. And on the right, instead of putting 43, I'm going to put 42.95. All right, and let's see what we get there if we match that. Sometimes the technology, using the different computers will get a little bit off, but it should be close. So our mean is going to be 37.62. Our standard deviation, 5.42. We have a lower bound to negative infinity. An upper bound, I'm doing 42.95. Maybe it should have been 0.5. Maybe you do 0.5 off either end. That's what I did before, but all of a sudden I was thinking that's a lot. So it's 5%. Let's do 0.5 and see what we get. Second function data, distribution, normal CDF. Those two things didn't change. But what I'm going to say is 42.5 and calculate that. That gives me 0.168, 0.816. I think that's... that one's a lot closer, so we're sorry about that. So I'm saying since we're not including the 43, we go up to it, we're just going to go up to 43 minus 0.05, which is 42.5, which is minus 5, which gives us 42.5, and that's what we're going to use for that. Sorry about that. I keep saying 05. Thinking 5%. We're taking off 5 off either side, yeah. Okay, let's try this with number 16 and see if we can get to the right answer. Number 16 says use a normal approximation to find the probability of the indicated number of voters. In this case, assume that 158 eligible voters aged 18 to 24 are randomly selected. Suppose a previous study showed that among those, 22% of them voted. What's the probability that exactly 40 voted? Excuse me. So I'm going to do the same thing. I'm going to find my mean by taking the 158 in times the probability, 20.22. And then I'm going to find my standard deviation, 158 times 0.22 times 0.78. And the square root of that gives me 5.21. And my mean here is 34.76, and I'm interested in 40 exactly. But since I can't really use 40 because 40 is just like a thin line. I do a little bit on either side, and I look at the lower range of 39.5 and the upper range of 40.5. And that's what's going to give me that, hopefully close to what they got, 34.76 and 5.21. Lower bound of 39.5, upper bound of 40.5, and 0.0462. Yeah, that's what we got. All right, so do that 0.5 thing on either side as you do that one. All right, that's actually 14 and 15, yeah, because I deleted that other problem. And so we're actually on to 16 right now. Okay, so a scientist conducts a hybridization experiment using peas with green pods and yellow pods. He crossed peas in such a way that 25%, or 142, of the 568 offspring peas were expected to have yellow pods. Instead of getting 142 with yellow pods, he obtained 146. Assume that the rate of 25% is correct. Find the probability that among 560 offspring peas, exactly 146 have yellow pods. So they already gave us the mean, 142, but we could go down and calculate that. I didn't do a very good job of writing that legibly. But 568 is our N, and then we're multiplying times our probability 0.25, and that's how they get the 142. So we know our mean is 142. Let me write that where we can actually read it. And then our standard deviation is 568 times 0.25 times 0.75, which is Q, 1 minus 0.25, and I get the square root of all that, 10.32. I put in the 142. I put in the wrong number to begin with. That's where we're seeing my mistake, but I fixed it before you ever saw it. So now I have those two values, and I'm wanting to know what's the probability of getting exactly 146. So if I do this, so I can kind of see what's happening, my mean right here should be 142. So I want to know what's the probability of getting exactly 146. And again, I'm going to do that thing where I subtract a half off each side to give myself a range of values to put in there, 145.5, 146.5, and I'm going to use normal CDF to do that. Second function data, go over normal CDF. I have a mean of 142. I have a standard deviation of 10.32. I'm going from these two values, so I'm going from 145.5 up to 146.5, and I'm getting 0.0358. They have a little slightly different numbers there. I may have rounded this and I shouldn't have or something, but I think we're fine. But let's look at what happens on the second part. What's the probability that at least 146 have yellow pods? What is at least? This is exactly. What would at least look like? Does that mean less than or greater than? Think about getting into a bar. You have to be at least 21. That means you could be 21 or more, right? So at least 21 means we're starting at 146 and we're looking at to the right of that. But for our continuity purposes, well, in this case, at least 146 means that 146 or more. My thing would be that it would be including 146 because it's not saying it's more than 146. Let's try it and see what we get. We're not matching their answers exactly, but hopefully we can get close. Our mean is 142. That I feel good about. Maybe I should have redone this one. I made so many mistakes on it the first time through, but let's say 146 to infinity. And that's not what they get. So let's try at least 146. Okay, let's try. I don't think it's going to make that much difference. I don't know what I've done wrong here. Let's do 146.5. I don't think that's going to make a big enough difference to actually match 0.33 now. Okay, so let me calculate this again. Second function, second function, square root 568 times 0.25 times 0.75. No, I'm good with 10.32. Which, let me go on for a second. I didn't get this result. I'm going to go back and look that up. But number 3 asks, which is the part that's important for determining whether the claim is correct or not? Well, do you see that I got like 0.3 something? I didn't get exactly that, but I got in that range. But 36, 35, whatever I had, it's way more than 0.05. Remember, if we have a high probability like that, then we say this is very likely to occur. If their statement is correct, this is 30% chance of occurring. If we get something less, 5% or less, that's when we say they must have made a mistake on their assumption. So part B is the part that we'd want to look at anyway. And when we'd say, okay, we say, well, there's not strong evidence to suggest they were wrong because our probability was way more than the 5% we would need to make that claim. Okay, so at least. All right, let me try one more time to do that, and we'll see if we just need to go look it up. 145.5.3672. I'm so close that I just feel like it's a different thing. They used a table and I used a calculator. But what I'm going to do, so you don't have to worry when you get home or you're doing this on your own, is let's go look at it. This would be number 16. Let's see if our information is calculated correctly here. So we're going to do this problem, and I'm going to kind of talk a little bit off screen, but let's say what the mu would be. There's 552, and we have a probability of 0.25, which they gave us again, instead of getting it, so that'd be 138. The standard deviation is going to be the square root of 552 times 0.25 times 0.75. And you can do that off the screen as well. 552, whoops, I need to do the square root of 552 times 0.25 times 0.75 is 10.17. Maybe I'll go out 3 or 4 places and see if that helps. So I'll go out to 10.1734. And then we want to know what's the probability of getting exactly 140. So exactly 140, I'm going to do 139.5 and 140.5 for my normal CDF. So you try that as well. Our mean was 138, and our sigma was 10.1734 is what I'm going with. My lower bound is 139.5, and my upper bound is 140.5. And I got to 4 places 0.0384. And so it accepted it even though it wasn't exact, which is what was happening over there. I wasn't sure how close I'd have to be. But the probability that at least 140, what I was saying is that if it's at least 140, I would go from 140 up. And let's see if they like that one. Second function, distribution. We have the same standard deviation and whatever. If I go from 140, it might be 140.5, which is what I originally calculated. But let's see what if they like that. If I go from 40, we have the idea of how to do this. Okay, so why are they throwing in this Z formula? That's because they're used to using a calculator where you have to normalize everything and you have to make your mean 0, your standard deviation 1. For our calculator, we don't need to do that. So we don't need to go through this this thing where we change it. But they do say to mark the 0.5 off of each side. So I didn't do that. So I'm going to do that again, which is what I started doing, but got something they didn't like, so I thought maybe. So it's going from 140.5 to infinity, 0.4029. They did not like that one either. And if I go from, I don't know, I'm not sure how they're getting that. Or if I do, I'm just trying to get, so when you do this, you're not trying to figure out how to get their exact answer. No. Oh, I see what I did there. That's bad. I entered something totally bizarre that time and just... I'll probably delete this part of the video so not everybody's sitting there and watching me do this. But, you know, like I said before, productive struggle is not so bad. So 138, 10.1734, our lower bound. These are changing. Okay, so that's how they did it. That's not what I got on over here, but the one that's important for determining this is B. And there is not strong evidence because we have a very high probability that that could happen by chance if they were correct about their assumption. So let's switch back over and I'll talk about how I actually ended up getting that correct. What they had, the one that was correct when I did that was for the 146. Remember, I calculated mu and I calculated the standard deviation. And then when I put this into the calculator, instead of using 146, I had to use half below that. So I used 145.5. Well, their numbers were different on the calculator, but that's the one that they accepted. So we want to go half below that and look at everything half below that or greater. And that's, yeah. So that makes sense, right? Because we're talking about 146. We can't go 146.5 because then the actual number we're talking about wouldn't be in our interval. We want to make sure that it's covered. So that's why we need to go to the half below it. So I should have thought of that earlier. But that's not the answer I got when I put that in. But like I said, they have a bit of tolerance built in so that if your answer is close, but it has to be pretty close. So that's why we had to put in the 145. So what I did was the 142, the 10.32, and then I would do 145.5 to infinity, and you can see that my answer didn't come out to be exactly as close as theirs. I got 0.3672, but they still accepted it because it's a range. We don't get it exactly the same. So that's that. Sorry about that, but I think I might leave that in there. It's good to see that, sometimes there's a couple of things happening. One, my calculator doesn't get the exact results that theirs do, but two, I made that mistake of not realizing that of course I have to be below 146 or else I'm looking at the interval that doesn't include the number that's important to me. So I learned something. Hopefully you learned something from that mistake too. And this last one we're going to do is just the same, only they're talking about girls being born, that kind of thing. Our N is 889. And our probability, they're equally likely, so it's 0.5. And our standard deviation is then 889 times 0.5 times 0.5. So let's get those two numbers, 889 times 0.5, 444.5. And the standard deviation is 889 times 0.5 times 0.5, which is 14.908. I'm going out one extra place there because it seems like maybe I'm not getting that. The probability of getting exactly 463 girls, we're going to look at 462.5 to 463.5. We're going to look at the numbers on either side of that as our range, and we have our standard deviation and things there. So second function data, we're going to enter 444.5 and 14.908, and then we are going from 462.5 to 463.5 and hitting calculate. And I'm getting point to four places, 0.0124 as my answer. That's exactly. And that one actually matched 0.0124. Good for us. The probability of getting 463 or more girls Now remember, again, I want to make sure that when I do this, I include the 463. So if here's my 463, I need to go back to 462.5. The probability of getting 43 or more, so we're going to go to the right like that, or more, right? So it's going to positive infinity. So let's do this one again. We're going to same mu and standard deviation, just had a total mind, and I'm going from 462.5 up to positive infinity, which is 1e to the 99th. That e I got from hitting the EE, that's an exponent button. And I get 0.1136. And they had 0.1136. Well, that's good. If boys and girls are equally likely, is 436 girls and 889 births unusually high? So unusual is what you get when you have this probability that's less than 5%, but we have 11.36, which means it could definitely happen by chance. So it's no, the 436 girls is not far from what's expected. 444.5 is what we kind of expected. 463 is not that far from what we expected, so that's A. And then which probability is relevant for trying to determine whether the technique is effective from part A or part B? Always, we don't want to look at one single birth. That could just be the exact. We always want to look at a range. That would be B. Based on the results, does it appear that the gender selection technique is effective? See how our results are more than 5%? We're saying, it seems like they're probably correct. That, wait a second. What are they saying? Gender is to increase the likelihood that a baby will be a girl. Oh, no, we just showed that it was about the same as normal, right? So they're trying to say that they're increasing the likelihood, and we just showed that this result right here could just happen by chance. So because this can just happen by chance, that means that we really can't say that their method did anything for us. So we would have to say that no, the probability of having 463 or more girls is not really unlikely. We had 11% chance of that happening. So we could say that's just a chance happening. And therefore, your method is not proven. It doesn't really disprove your method, but it doesn't prove it yet because we're not seeing anything that looks out of the ordinary. All right, in a study of 215,438 cell phone users, it was found that 22 developed cancer of the brain or nervous system. Assuming that cell phones have no effect, there is a 0.000146 probability of a person developing cancer of the brain or nervous system. We therefore expect about 32 cases of such cancer in a group of that many people. Estimate the probability of 22 or fewer cases of such cancer in a group of that people. Well, this is they already gave us the mean, but we can calculate it just so you can see how they got that. I am just hating this pen, but I'm stuck with it. So I'm just going to keep going. 215, 438 times 0.000146. And if you do that, 215, 438 times 0.000146 gives you 31.45, or about 32. Because we're talking about people. My standard deviation is going to be the square root of 215, 438 times 0.000146. 1 minus 0.000146 is 0.999854. That's going to give me my standard deviation. So I have second function square root of 215,438 times 0.000146 times 0.999854, and that gives me about 5.608. Okay, now I have those two important numbers that I need, and then I go back and say, what's the probability of getting less than or equal to 22? So the mean is 32. So 22 is over here, right? So I'm looking at over here to the left. And I want to look at, so that I include 22, I want to look at 22.5, so that as I go to the left, 22, my important interval, my important discrete number there, is included in that thing that I'm looking at. So let's do that. Remember, you can clear out all this crap by just going to on, clear, clear, and you don't have to worry about it, but I didn't do it, so 5.608. And then we're talking about negative infinity up to 22.5. And I calculate that to get 0.0. Well, let's read the root of 23 or fewer out of 254, 438. 215, 438. Oh my heavens. I did not get their same answer. I don't want to do this whole thing over again. Okay, anyway, let's take a look at my result, at their result here. That's what they got, and I may have to do this video over because I have just not sure why my calculations are not coming out, and I just have to think that it's about the calculator, but I was off a little bit here again. 22 or fewer is from 22 over to the left. So that's negative infinity up to 22. We're going to do 22.5. We have our mean and we have our standard deviation. Now, I don't know, maybe I shouldn't have rounded it to 32 like they did. So what was that answer? It was 215, 438 times 0.000146, 31.45. Because they gave us that number, I thought maybe they were wanting us to use that, but maybe they weren't. I haven't obviously done these problems before on this thing, and sometimes when you first work these problems, you're just trying to figure out what the computer's wanting, where do you round things and that kind of thing. So this time I got 0.0552, which I think would be close enough. Either way, I got this answer by, I did not round that to 32 this time. I left it at 31.45, which made the difference. Okay. So, what does this result suggest? This is, what were the media reports? The media reports, that cell phones cause cancer of the brain or nervous system. So what we found, this is a little confusing, but what we found is that these results, 22 or fewer, our results are not really unusual because we have 5% or more, so it's not unlikely for this to happen by chance. Since it's not unlikely to happen by chance, then it's probably true that this is the actual probability of that happening. So it's not increasing because of cell phones. So 22 fewer cases is not that unlikely, but we can see the probability is 5% or more. That's all we have to always look at. So it's not, it could happen by chance. And so these people that are getting it by chance because there's a chance that anybody could get it. Here's the chance, and this is happening at that rate. And so just because they use cell phones does not, we have not shown that that rate has increased because of that. So I would go with A, which is what the answer is there. Okay, that's the end. Maybe if I have time, I'll come back and do this video again, because it does feel like I had a lot of weird little stuff going on. But anyways, for today, I'm stopping. Have a great day.